All right, according to my clock, that's about the right time, so we'll get started. I've got a lot of things to cover today. Should be something for everyone in the room, so hang on tight and we'll jump right in. Today we're going to talk a little bit about how we can build efficient dynamic languages on the JVM. Various definitions of efficiency, of course performance is one of them, but we'll go through a few different areas that I think are important for language designers and developers on the JVM. There's my basic contact information. Feel free to reach out to me directly. I am a JVM developer now for 20 years. I've been a Java developer since the beginning, so 30 years of Java. Currently working for my own company, Hedius Enterprises. We provide professional support and consulting for JRuby users, and now expanding to try to bring what we've done for the JRuby project and the JRuby language to your Java applications and your libraries out there in the world. Of course, Slido, like everybody else, we're going to be doing questions here. So here's the QR code if you need it, and we are in room 11. You can also feel free to contact me directly with any questions you have offline. So, dynamic languages on the JVM. So it really turns out that the JVM is an excellent target for all kinds of languages. Of course, statically typed languages like Scala work very well. Kotlin has carved out a huge portion of the Java community. But dynamic languages also work really well. We have an optimizing, profiling, runtime JIT that can take our code and turn it into fast native executables. We have the best garbage collectors in the world. Dynamic languages have traditionally struggled with having poor garbage collection, poor memory management, and a lot of allocation, a lot of objects that they need to deal with. But there are some challenges along the way. And it's these challenges that have helped push the JVM forward. Us working on JRuby, other folks working on implementations of JavaScript and Python, we have pushed the edges of the JVM, and we've also been able to bring the JVM to a much wider world. There's an entire community of Ruby developers out there that know what the JVM can offer because of projects like JRuby. And that's good for us as Java developers and JVM users, and it's good for the wider development world. So what are our requirements here? One of my primary requirements for any of the projects I work on is it needs to work on any JVM anywhere. I don't want to have to require a specific build or a specific vendor or a specific custom VM to run the code I'm going to write. It has to be, we have to keep usability in mind. Startup time should be reasonable. We should not have to make users wait for command line because there's many different workflows out there that depend on fast command lines. We don't want applications that take forever to warm up or take way more memory than the original implementation. We don't want people to have a bad experience coming to the JVM from their original language implementations. Of course, we want to be able to interop with other JVM languages. Clearly, that means being able to call into Java, but ideally being able to interop with Scala and Kotlin and other dynamic languages. So that's a key point on the JVM that we can bring to users of these languages. There's also a whole world of native libraries out there that's just starting to be exposed to JVM users, and we'd like to have that integrated into our languages as well. Performance, of course, is a key characteristic. We'd like that our JVM implementation of these languages performs at least as well as a native implementation, and ideally, bringing the JIT to the project, bringing the GC to these users, we should be able to do better than those native implementations. And then, of course, all of the JVM tooling we have, we'd like that to integrate well with our language, so we can use the same profilers, the same monitoring tools, and the same set of features that the JVM users have become used to. So, what does that leave for options here? So, of course, OpenJDK on the hotspot VM, the standard Java that pretty much everyone's going to be running, this is a clear target for us and probably the safest place for us to start working. It's got good, stable performance characteristics. It's been developed over 30 years now, 20 years of the hotspot VM, and definitely a good target for us. There is also the IBM OpenJ9 VM, provides different garbage collector options, different JIT options, offline JIT, ahead of time compilation, a whole other set of features, but still based on OpenJDK and still very much compatible with the spirit of the Java platform. GraalVM is a newer option for us. So this is OpenJDK, basically partially hotspot runtime and using the Graal JIT to do more aggressive optimizations. Now we're going to stay away from GraalVM specific features because we want to be able to move to other VMs on odd platforms, embedded environments, and using things like native image that limits our set of JVM features, or using truffle, which is kind of specific to the GraalVM. We're going to stay away from those for now. This even opens up the possibility of developing for mobile devices. The Android runtime has evolved over time to become OpenJDK based with sort of a hybrid hotspot ahead of time JIT backend optimized for embedded and mobile uses. And we've seen people use JRuby on Android to do point of sale devices, advertising kiosks, and so on. So a quick survey of the languages we have available today on the JVM and where they are in their status. The old classic here, Rhino. How many Rhino users have we had out there? Sometime. Yeah, there's a few folks around. Some of us remember it. So this one goes way back. This is Java 1.1 time frame. Norris Boyd decided that we needed to have a JavaScript implementation on the JVM. It's a very simple runtime. It has either an interpreter mode or sort of a lazy ahead of time JIT. Compiles things as they run. It's still very useful for lightweight cases, but it has fallen behind on compatibility with JavaScript features. It's not using a lot of modern JVM stuff. I would love to see this revitalized and redesigned, reimagined for a modern JVM. On the other side of the coin, we have Nashorn, which is designed with modern JVM features in mind. This came along around 2011, kind of Java 8-ish as far as modern JVM features. Heavy use of InvokeDynamic, aggressive optimizations. This is probably the best performing JavaScript of any of the pure JVM options that are available. But because of these aggressive optimizations, it ends up feeling pretty heavy. It generates a lot of JVM bytecode, a lot of JVM classes, and so for certain use cases, it may be a little heavier to use than something like a Rhino. Again, this has also kind of fallen behind on JavaScript and JVM features, but it's out there, it could be updated, and I'd love to see that happen. Then, of course, there's Python. Python now being, according to many sources, the #1 programming language out there. And yet, the only implementation of Python we have running on the JVM has been largely abandoned years ago and is still stuck way back on Python 2.7. There's also difficulty supporting the Python ecosystem. A lot more native extensions, a lot of entanglements at the native level with the way the runtime works. There's great potential here, but there's a lot of work to update for newer versions of Python and modern JVMs. Still, I think it would be important for us to be able to bring the Python users over to the JVM so they can at least use their knowledge of Python to build JVM applications. And of course we have Groovy. This is one of our homegrown dynamic languages for the JVM. Came around in about 2003, inspired in part by Ruby. Mostly these days, Groovy code I see is generally used in more of a static style. It uses all of the same Java types, it uses a few dynamic features, but over the years, Java itself has adopted some of these. We have lambdas and closures now. We have some of the type inference that Groovy provides. So I'm not sure what the future of Groovy is as a JVM language, but I'd love to see it revitalized again and brought up to Java 21 to 24 feature sets. So our model for most of the discussion today will be JRuby. This is a pure JVM language. We run on any JVM. All of the ones that I listed work very well with JRuby, and we have had users on all of those platforms, including a lot of weird ones. We have always on, always available Java integration. Ties in Java libraries so you can call them directly from Ruby. Excellent performance. We JIT code down to JVM bytecode and use InvokeDynamic to optimize dynamic calls. We're always playing with the latest JVM features. The most recent release of JRuby, JRuby 10, now requires Java 21. And so we are starting to leverage a whole bunch of features that we've had to put on hold for years. We also have built-in native library support, a very nice Ruby DSL for pulling in native libraries, calling functions, and integrating it into a Ruby application. Active development, lots of users out there. This is just a sampling of some of the users of JRuby over the years. The kinds of uses we have. Of course, people want to scale web applications better, but packaging up an application without any other native entanglements, without any extra requirements other than a JVM. We have mobile and embedded users, people building Android applications. Lots of exotic platforms where the JVM runs, but standard Ruby does not. Scripting support, of course, if you want to use a Ruby language to script your Java application. And then just bringing the entire Java platform to Ruby has been a great benefit to Ruby developers around the world. So let's jump into the implementation of JRuby and the challenges that we have tried to meet over the years. Starting out with an area that I'm not super excited about, parsing the actual language itself. So this is a fairly mundane process. Anybody who's done Computer Science 101 has had to do a basic parser. We're going to read in our source files. We're going to tokenize it into literals and keywords and functions and whatnot. We translate those tokens into an abstract syntax tree. And now we have a representation of the flow of the program, how the code is going to be represented. We can even start interpreting at this point. We could walk our AST, do the operations as they come up, and we're basically got our language brought into the JVM as a large graph. Now, depending on your language, this can be a simple process, or it can be a very complicated job to do this parsing. So this is a representation of JavaScript. It's a fairly regular language. You can see there's some clear branches here, nodes that are grouped fairly local to each other. Pretty easy for us to see how we can parse through that code, and not too much variability in where these different constructs come up. By comparison, this is Ruby, and it's actually an older version of Ruby. It's much more complicated these days, but almost every node is connected to every other node. The parser has lots of context sensitivity. There's very difficult processes in order to make this Ruby code turn into an abstract syntax tree, and this has been one of the biggest challenges for JRuby over the years. So as I mentioned, it's a very complex, context-sensitive grammar. Historically, there has only been one complete parser out there, an LALR parser, originally based on the Bison grammar, ported to the J generator for JRuby, which is essentially Bison for generating Java code. More recently, we've actually had a Ruby community member that did a handwritten recursive descent parser. This has allowed us to start sharing the parser with the standard Ruby implementation. We now can run the exact same parser code that the regular Ruby does. So this has reduced our load on tracking language features over time. So parsing for you. I would definitely recommend trying to keep a language that you're developing simple. If you must use a language that exists out there already, or you're bringing an off-platform language to the JVM, try to use the original parsers as much as possible. If you're designing a new language, stick with parser generators like Antler or Java CC. Try to keep your grammar regular. Try to avoid some of the complexities that are in Ruby. As much as Ruby folks love the language, we all accept that it is a very complicated grammar, and it's a big challenge for getting Ruby on other platforms. For a little more information on this process, the JVM JIT for Dummies talk will kind of show you how the JVM brings in code, how it processes these languages, and how it actually optimizes under the covers. So, we've got our AST, we've got our representation of our dynamic language brought into the JVM. Ideally, we want to compile it into something that optimizes and performs well. So compiling Ruby code. This has been a tricky bit for us. All Ruby code, like in the Python world to some extent, in the JavaScript world, usually lives on disk as source code. So every time we start up the application, we must load all of that source, parse it all, compile it, and start executing. And those are a lot of steps for us to get up and going. Ruby users just will not tolerate a separate compile or build step as part of their workflow. They want to be able to edit in one browser, run a command, and it's executing immediately. On the JRuby side, our goal is to eventually get to JVM bytecode. That's how we're going to get the best optimization, but we also want to have reasonable startup time. Adding another stage to that execution pipeline just slows down the process of running code. So for JRuby, we actually decided to do what was called a mixed mode runtime, very similar to the way the JVM works. What we found is that when you load up all of these Ruby sources, all of these libraries, 90% of the code that gets loaded never is called. Only a small portion of each library is actually used. Methods that are called early in the boot process may only be called a few times. So spending a lot of effort on optimizing them doesn't make sense. So our choice was to interpret code at first, originally using the abstract syntax tree, now compiling to a simple bytecode format we have, and then lazily JIT compile into JVM bytecode later when we see that methods are hot. A bit more graphical view of this. We have our Ruby code coming in on the left. We parse this and compile it into our internal Ruby instructions. And then we have an interpreter that actually executes our Ruby IR directly. This interpreter will run for a while, the JVM will heat it up, and it'll actually perform reasonably well, comparable to some older versions of regular C Ruby. Eventually, we'll realize that some of these methods are hot. They need to be optimized better. And at that point, we turn it into JVM bytecode. We do our own internal optimizations. We use InvokeDynamic to make sure dynamic calls are fast. And then the JVM continues this process. It interprets the JVM bytecode for a while. It does some initial compilation to a level 1 compiled format, and then it continues to profile and optimize as it goes. So what is compilation for you, building your language on the JVM? Well, the big question to start with is whether you want to have an interpreter as part of your language. For some small language that you just want to get up and running quickly, that may be the best option. And from an interpreter, you have other options. You can start there and move on to a compiler. You can move on to a truffle language. Start with the interpreter because it's the easiest way for you to get a hold of how your language should work on the JVM, and it may end up being one of the quickest ways for users to get up and running. Once you do start compiling, the standard library that almost everyone uses is the ObjectWeb ASM library. Now we've got, on Java 24 and higher, a very similar API built into the JVM called the ClassFile API. We're just starting to look at using this in JRuby now that we're on modern versions of the JVM. So we'll walk through a little bit of the ClassFile API just to show how easy it is to create JVM bytecode on the JVM now. So we start out at the top. We're going to get the raw bytes of our bytecode. So we create a class file with no options. The of creates a class file. Now we're going to build it. And we have this DSL-like, this builder-like structure. So we want to make the myPackage hello class. So we get the class descriptor that represents that package and class name. We have a public class. This is going to be one that anybody can call and instantiate. Now we are within our class builder, so we want a new method body. In this case, we're doing our constructor, which is the init method in a Java class. The init method returns void. It is a public method, so people can construct this from outside of our package. Now we actually get into our bytecode. We load the 0 variable, which is the self, the this value, and the constructor. We are going to do an invoke special here to call out to another object. Yes, call the init. We're going to do a super call for here. And then we're going to return. So a very simple method, a very simple class, but now an API that has a nice flow to it, built into the JVM, so anybody can start generating bytecode without having to pull in a third-party library. So for a little more on how to generate bytecode, how to understand what the JVM is doing under the covers, I have a talk out there, JVM Bytecode for Dummies. You can take a look at this. Let me know if you have any questions. The JVM bytecode has not changed significantly in the past 15 years or so since adding InvokeDynamic. So once you learn how to do this, you're going to be able to build JVM bytecode, generate code for JVMs long into the future. So now, we've got our JVM bytecode, but mostly this is going to be statically typed. When we make a call, we need to provide a specific class, a specific set of argument types. But we're talking about dynamic language. How do we make this dynamic? And that's where we get into the real magic of dynamic languages on the JVM, InvokeDynamic, the feature that was brought in with Java 7. InvokeDynamic gives us a way to provide programmable method invocation for the JVM. Rather than saying we want to call a specific class with a specific set of arguments, we let the JVM call back to us. We provide a new way of looking up methods, a new way of converting arguments. The InvokeDynamic bytecode points at our bootstrap method. So when it comes time at runtime to call this method, the JVM says, what am I supposed to do here? We go out, we look up our method. It may be a Java method out there. It may be a Ruby or Python method. We wire it together with method handles, wrap up a function pointer in some adapters, and then plug that back into InvokeDynamic. Method handles basically provide a way to grab a function pointer to some piece of code out there, adapt it to our InvokeDynamic call site, and then the JVM can optimize that as if it was a pure Java call all the way through. A little easier to see with more of a graphic representation. It's kind of like a switchboard. So we have our InvokeDynamic bytecode up here. The JVM comes in, makes a call, and it's got InvokeDynamic. It doesn't know where to go from this point. The InvokeDynamic bytecode calls out to our bootstrap method. It's like our switchboard operator here. The switchboard operator knows how to find the right place for this call to go, plugs it into the switchboard using method handles. So our method handles take the arguments that are coming in, takes the name of the call and the object we're calling against, and finds the right method pointer to wire into this call site. We pass that back to the JVM in our InvokeDynamic bytecode. And from then on, the JVM can make this call directly and optimize it at the native level as if it were a static call. So dynamic invocation on the JVM done as fast as real static Java invocations. The rest of this can be swept away. If we need to rebind it later, we can, but we can get full performance out of dynamic calls by wiring up InvokeDynamic. So this is an example of the performance improvement we saw in JRuby when we started to use InvokeDynamic for our method calls. Previously, doing all of this plumbing ourselves each time, trying to cache things on our own, trying to go do the lookup on our own, but easily getting 4 times performance improvement on some simple benchmarks. In typical applications, we expect InvokeDynamic does a 3 to 5 times improvement in performance for Ruby applications. So how does InvokeDynamic work for you? Well, the method handle API is fairly low level. You can go and look at the Java docs for it, but it's kind of complicated to get into the details. I would recommend looking at a library I've written called InvokeBinder. It provides a more builder-like structure. You start out with a return value and a set of arguments. You make your adaptations, insert an argument here, delete an argument there, restructure the calls, and then finally call into a target method somewhere on a class. It generates all of the method handle code for you, and it's much more readable and flows a bit more like typical programmers would want to read things. InvokeDynamic is even lower level. I've provided a link here to an early blog post I wrote on how InvokeDynamic works. Kind of brings you through the story and the design of how InvokeDynamic was created and what problems it's meant to solve. So at this point, we've got our application, we've got our language parsing, we've got our compiler working, we can do fast dynamic invocations, we can run our code. And with InvokeDynamic, we can actually run code very fast. There are benchmarks on JRuby that can be comparable to Java performance when run in the right configuration, when we're not using a lot of the weirder Ruby features. But because of all of this work that we're doing, we kind of start up a little too slowly. And this is now the #1 problem. It really has been the #1 problem for JRuby and for off-platform language users coming to the JVM for many years. So let's talk about startup time and how we can solve this problem. So despite all of our tricks, all of our interpreters, all of our mixed mode execution, we're still far, far away from the speed of CRuby as far as startup. Running quick commands is considerably slower. The interpreter helps, no doubt about it. This was definitely the right choice for us. If we were trying to compile all the way to JVM bytecode, the situation would be even worse. And for anyone who's tried to run Nashorn as a command line application, you can see how much that aggressive optimization, generating all that bytecode, slows down the system. So let's take a look at how bad this is as a baseline. Here's CRuby, designed for startup time, designed to be used as a command line workflow for almost everything you do. 64 milliseconds for a simple hello world here. And then JRuby comes in, 18 to 20 times slower for a hello world. And now this isn't entirely our fault. All of the JRuby code starts out cold. That's including our parser, our compiler, the AST itself. Our interpreter even starts out cold because that's just JVM bytecode as well. Once you actually get JRuby up and going, we can run hello world in a loop extremely fast. But those first couple calls are going to be slow. So how do we get around this? Well, how many people remember client and server mode for the JVM? This goes way back too, right? Well, it's back. We have added a dev flag to JRuby, which basically turns off a lot of optimizations, simplifies the way that the JVM does its own optimizations by limiting it to that first stage of JIT compilation, and switches to a garbage collector that has a bit faster throughput early in execution. So if we throw our dev flag at this, okay, starting to get there, almost down under a second here. So that helps. Just turning off optimizations can actually improve our startup time significantly. Now the JVM itself has continued to evolve and add features for startup time. And the two that we're most excited about now are called AppCDS, Application Class Data Store, and Project Leyden, which is going to do sort of a super AppCDS, caching class data and JITted code over time. Here's a couple of the important flags for AppCDS. You can throw these onto any modern JVM and try it out. Automatically will profile your code a bit, try and preload and pre-cache classed information, parsed methods, parsed bytecode, and save it off to a file that you can use to start up quickly the next time. We have this integrated into JRuby's launcher so that JRuby users now get the benefit of AppCDS just by running JRuby in the normal mode. So let's see how we're doing here, okay? We're down to about a second. Now we're getting into sub-second ranges. This is starting to get at least acceptable for a command line workflow. Under a second is pretty good. We're still not down into the 100 millisecond range that we might like to be, but we're getting there. When we add in Project Leyden, again, another incremental improvement. And Leyden is actually under really rapid development right now. I'm sure that this is probably closer to 0.5 seconds now with the most recent builds. Looking forward to seeing how far they can take this and how much of that optimized code we can cache between executions. So we want to go even faster, right? We're waiting for Leyden. It's coming along, but it's not quite where we want it to be. What if we could actually go up to warp speed here on executing our startup time? The other project we've been looking at is called Project Crack, one of the most unfortunately named OpenJDK projects. Coordinated restore at checkpoint. The idea here is that we can run our application to a particular point, probably warm it up, load in some important code, exercise the pages or the actions that we find are most important, and then snapshot at that point, save it like we're hibernating a computer. We dump that out to disk. Next time we start up, we can jump right back in at that point. We restore that hibernated process into memory. We continue executing from that point with all of those optimizations, all of that data already loaded. This is still primarily a Linux technology. It uses a feature called coordinated restore and checkpoint and restore in user space, CRIU, specific to Linux. But folks at Azul and others that are working on Crack are trying to find a way to bring this to more platforms and not have this dependence on the Linux kernel and CRIU. There's also some very sharp edges here. I/O channels that were open before in the process need to be restored and reopened. Resources that you've allocated may need to be reallocated again, or locks be reacquired. And there's some trickery around PIDs and thread IDs that are still being worked out. But how well does this work? It sounds pretty good, right? So we've got our steady progression of improvements on startup time here. Let's throw crack at this. Now we're starting to see some real improvements. Can run a standard Ruby application started up from the command line almost as fast as regular C Ruby. And the magic part of this is that we actually could take an entire Rails app, boot that whole thing up, warm up all that code, get it ready to go in production, and then immediately checkpoint it, throw it to our production server, and start up with a hot instance right away. Really exciting stuff. I'm looking forward to seeing where this goes. So startup time for you. AppCDS is probably the easiest way for you to start speeding up the startup time of your applications right now. Leyden is going to take that to the next level. So follow the project. There's a lot of work going on, and they're very eager to have people try this out and report back. In the future, Crack or Warp or something similar may be able to freeze dry and store off your process, jump back into it in the future, but it's very specific cases right now that this might work for. I have done a couple blog posts. This one is on a comparison of Leyden's AOT cache with the existing AppCDS features. I also have another post on Crack that shows JRuby integrating Crack. We actually provide command line arguments for users to start up a Ruby application and checkpoint it, and then jump back in and restore it. Trying to expose as much of these cool JVM features to the Ruby world as possible. So another challenge for us in the Ruby world, there's this whole set of Ruby core classes, and one of the most complicated ones for us to deal with has been representing Ruby's strings. So let's do a little review here. What does a string look like in Java? Well, traditionally, the classic string in Java was just a string object that wrapped a character array. So this is always going to be UTF-16, not particularly efficient if all you have is 7-bit ASCII or 7-bit encoding. So we're wasting a byte for every character there. More recently, the string implementation has been adapted to allow either a 7-bit representation, a Latin 1 representation of your string, or UTF-16. A lot of magic under the covers to optimize that, but still immutable, still fairly static as far as how strings are represented. Now, if we look at how strings are in Ruby, there's a lot of challenges here for JRuby. Number one, Ruby lets you have strings of arbitrary encodings all over the system. They don't necessarily have to be transcoded into a UTF-8 or into a UTF-16. You might have a string in Latin 1, you might have another string over here in UTF-8, and you might have strings in UTF-16 or 32, all existing at the same time in this runtime. It's mutable by default, so we've had to build our string to optimize mutability and splitting and use copy on write to avoid copying buffers as often as we might have to if we were doing a fully immutable string. And again, complicated logic under the covers to try to optimize all this and make it work well on a modern JVM. So here's what we've got for our JRuby strings. We've got a custom string implementation. We wrap an object we call a byte list. This is sort of like a string builder, but with bytes and with different encodings allowed. Allows us to mutate the string in place, share a buffer across multiple byte lists for more efficient use of memory, and then we have an encoding object that represents how those characters are encoded in that byte array. Now, because we have our own string implementation, this also necessitated us building our own regular expression implementation. We ported a library from the C world called Oniguruma. Our library is called Joni, J-Oniguruma. And this allows us to do regular expression matches directly against a byte array of arbitrary encoding. It's a regular expression engine that has pluggable encoding support and pluggable regular expression grammar support. Now actually being used in Nashorn and other JVM projects to provide a way of doing regular expression matches against raw bytes without having to decode them into a string with all of the overhead that comes along with that. We also had to do this because there's certain deficiencies in the standard Java regular expression implementation. For example, if you want to do an alternation here, an A or B, any number of those over a very long string, Try to run this on any modern JVM up to Java 24, and you're going to get a Stack Overflow. The way that the regular expression engine on the JVM is implemented, alternations like this tend to recurse. And so if you're matching over a very large input, you are going to blow out the stack very quickly. This turned out to be important for us because people in the Ruby world like to use regular expressions for things like matching JPEG headers in a very large data stream. Once we had a complicated enough regular expression and enough input data, it would just blow the stack and we couldn't even run the application. So, for you, these libraries are available and they're standard Java implementations. The JCodings library provides a way to transcode byte-to-byte arrays, never have to go through a UTF-16 character. You can leave bytes in their original format that you've read it off disk, such as a Latin 2 for Polish here, or any other of the 7-bit encodings. It's designed on the same encoding system that CRuby uses, with an optimized transcoder, optimized internals, specially designed for the JVM. And then we have our regular expression engine, Jony, which can work again directly against byte arrays, directly against raw bytes from the system, rather than reading everything as a string and transcoding it to UTF-16, putting it into a string object, and possibly dealing with regular expression problems on the JVM. You can use Jony, you can do this byte matching directly, and it's optimized and works very well. This is a talk I did on Ruby strings in JRuby and what the JVM can learn from them. We're obviously very excited to see that Java's string has started to evolve some of these features, representing more than just UTF-16. I would love to also see UTF-8 a representation inside Java strings. In the rest of the world, that's kind of become the standard encoding everyone depends on. I think we should be able to bring UTF-8 strings directly into the JVM without any additional copying and overhead. So I mentioned Java integration, or JVM language integration, being important. So Java integration is probably the key feature for JRuby users. It's one of the things that really draws in Ruby folks that want to run on the JVM. And what I've seen is that a lot of languages out there provide a sort of polyglot interface. You need to request access to a class reflectively. You need to go and ask for specific methods. You basically need to do all of the reflection logic yourself to do this invocation. That's not something that a Ruby user or a Python user is going to want to do. They want to be able to come into the implementation on the JVM, load in those classes, call those methods, and access those fields as if they were just a regular Python or Ruby object. That's exactly what we did with JRuby. Old versions of JRuby had this sort of polyglot interface, but today you can import Java classes directly into a Ruby script. You can call all the methods as if they're Ruby methods, and we do all the magic of converting and finding the correct Java method targets for you based on the arguments that you pass in at runtime. So I'll walk through a little example here of using the swing library from Ruby. Here we have our accessing of the JFrame and JButton classes. This is all pure Ruby code here. We provide some shortcuts for the package accesses, so anything in Java, JavaX, org, or com, you can just start calling directly. Otherwise, we have a little namespacing system that we use to get at that. A bit of magic here, we convert the Java methods into more Ruby-like methods. So add action listener with capital A and L becomes the underscore version for Ruby. So it flows with the rest of your Ruby application. Here, we're creating an action listener. We don't want someone to have to construct a new action listener implementation, pull the interface in, define the method. Like a Lambda on regular Java, we can just pass in a closure here, and now this will become our action listener. A bit more magic, adding the button to the frame. Of course, this is get content pane, but JRuby's smart about it and turns getters and setters into attributes so that you can just say get frame.contentPane to get that content pane out of it, and then add our button. And again here, this is set default close operation. We turn it into an attribute setter for Ruby. And visible is true. Now we have our window, and we click it, and of course it calls right back into Ruby and works like we'd expect. Nice, clean code, very much the way that Rubyists would expect it to look. And this is what Java integration in your JVM language should look like. It should feel like you're still in the host language, the normal language, and not having to do this foreign interface. So, like I say, Java integration for you, the most important thing is it should feel natural. You shouldn't have to know how Java works and how to find these methods and what these types are to make basic calls and basic usage of the API. You'll notice there was almost no declarations of any types in that Ruby code. Just call into the frame, call into the button, we'll make it work the way that it's supposed to work. And then, of course, we use InvokeDynamic to wire all of this together. None of that magic requires slowing the program down. We can optimize it directly. The calls to action listener, the calls to set visible, all become optimized and inline just like they would in a normal Java application. So integrating languages, of course, nowadays we also recognize that there's a whole world of native libraries out there. So what are we going to do for native integration here? In the Ruby world, there's a lot of behavior that depends on native libraries, native features. There's a lot of dependencies on POSIX behavior. We have to be able to provide the same sort of interfaces to Ruby users, or the applications just aren't going to work. Ruby has an extension API that's very invasive, has direct pointers and memory access. Ideally, we want a way for JRuby users to call native libraries without writing JNI code. So we introduced a library called the Java Native Runtime. This is a set of libraries for binding and calling native libraries from the JVM. There's a whole set of tools here. Up at the top is the lowest level piece, the JFFI, which just wraps libFFI, pulls libraries and functions in. JNR FFI is similar to, some of you may have seen JNA, Java Native Access out there, provides a way for you to bind those functions to a Java endpoint, a Java interface. And then we've built in a whole bunch of predefined libraries. We have a whole set of POSIX functions pre-bound for you using JNR. We have a native channel that uses native reads and writes and native select operations. We had a Unix socket library long before one came to the JVM. We have a process builder that lets you load up a process and select on those streams, so you can actually do an interactive subprocess on the JVM. Now, on the Java side, this has evolved into Project Panama. This is something that we've been asking for many years. Panama now brings this sort of foreign function interface to the JVM. We can allocate native memory, we can call native functions, and the JVM optimizes it as well as it can. You'll see native code from your Java application called directly into a C library, rather than going through all of the overhead of JNI that we used to have. It also comes with this amazing tool called JExtract. JExtract uses LLVM as a library to generate all of your Panama code. You point it at a header file, and it spits out a Java library that can call that library for you. All you have to do at that point is import the library and start using your native library directly. So an early success story here, the SQLite wrapper for JDBC. We use this in JRuby because it's the typical way you get started with Rails development. And so we needed to be able to support SQLite as well. But the existing version uses JNI. And JNI has a lot of overhead that made it not feasible for using in high throughput use cases. The Panama-based version of SQLite JDBC is in development now, but already showing twice as much performance, much less overhead than using JNI, and we're continuing to see ongoing improvements in Panama and a lot of these libraries starting to bind with it. Panama available as of Java 22, so you pull in Java 24 or the next LTS, and you can start using Panama in your applications. I have a little intro talk to JNR here that you can pull down, basically how to use it to bind native libraries, a little bit of more of a walkthrough through all of our utilities, and then of course there's lots of resources out there for Panama and how you can get started generating this code and calling native code from your own Java applications. The last section I want to cover, and this has been another challenge that came to us from the Ruby world, is virtual threading. And in Ruby, the virtual threads are called fibers. So fibers are virtual threads for Ruby, basically like a little micro thread. If we want to start up a little task that's going to make one blocking call, we can start up a fiber and come back to it later. Cooperatively scheduled, we resume when we want to, we give up control when we want to. Increasingly used to provide high concurrency for blocking operations without holding a single native thread and making it wait on an I/O call or a lock. So a little flow through of how this actually works in an application. Here's our execution flow here. In a typical application using threads, we've got our first thread here. We're going to accept a socket off of some network. Now we're going to wait for I/O. We're waiting for a request to come in. At this point, this thread is blocked. It's not going to get any work done. Eventually, that request comes through. We can handle it. We've got our request. We handle the request. OK, now what we need to do is send a response. OK, we've sent our response. We've put it on the I/O line. Now we're again waiting for more operations to happen, wasting this native thread during these downtimes. If we do this with fibers or with virtual threads, so we've got our native thread over on one side. We can do this in a fiber. We handle it, we pull it, we accept our socket, we wait for our request to come in. While that's happening, we can actually jump over to a different fiber. We can hand it off. We don't need to use this native thread right now. This fiber can accept a different socket, wait for a different request. While that one's waiting, we jump back to our first fiber, back to our first virtual thread. Now we can handle the request. Now we can send our response, and so on. So we can make the most use out of the native thread, the heavy part of concurrency, without blocking it and still keep work moving forward. So fibers on JRuby. Before Java 21, before Project Loom, we had to implement this using a native thread for every single fiber. And of course, this was bad for performance, but it also didn't scale to the levels people wanted. We could only do a few hundred or maybe 1,000 fibers before the system would just complain about too many native threads. We also had the issue where if somebody ran a fiber for a little while and walked away from it, well, it's still a native thread. That's still a garbage collector route. We can't clean that up, and we would end up leaking a whole bunch of resources and eventually blow up. It just didn't scale, and it wasn't working for us. But on Java 21 higher, we have Project Loom now with virtual threads. In JRuby, every fiber has a virtual thread. The scheduling all happens automatically. Cleanup is much easier, and we can literally run tens of thousands of fibers now. This is probably the most magic to me. This is the only change that was required in JRuby to switch from our thread-based implementation to a Loom virtual thread fiber. Suddenly everything just worked, and we can spin up tens of thousands of these. We can look at even performance is quite good for this. So 10 million times of starting a fiber and letting it finish. 10 fibers, 100 fibers, 1,000 fibers, 10,000 fibers. Now here up to 100,000 fibers, still cranking through all of these requests using only a handful of native threads and performing very well. Not until we get to like 1 million fibers do we start to see things slow down. And this is more about the amount of fibers and virtual thread state that's being managed in memory. But amazing that we can get to this point. And even CRuby can't get up to 1 million without starting to fall apart. So virtual threads for you, of course, Project Loom shipped with 21. Lots of great talks out there, including here, the Organized Chaos talk by Conrad. Check it out. You can see how virtual threads are being used to do better concurrency today. Really exciting work, and I'm so happy that this has finally come to the JVM. So wrapping up here, now it's your turn to go out and play with some of these technologies. These are exciting times on the JVM. It continues to be a rich platform with amazing features. No other runtime out there that can do all of the things that the JVM does. So build a new language or help out an existing one. We'd love to have you work on JRuby or help me get JSON, JavaScript implementations going again. Play with this code generation. Play with the dynamic calls. Take a look at the talks that I've provided and how you can start optimizing code and optimizing languages on the JVM. And You know, a lot of folks are worried about AI generating all the code. AI is taking all of our jobs. But no AI or LLM can replace what we've got in the JVM. You generate that code, it's still got to run somewhere. And you've still got to know what features are important for your language, for the code that you're generating. Future-proof your career by learning how the JVM works, how all these new features fit into an efficient application, and you'll definitely be able to keep working on some cool stuff into the future. If you need any help with this, that's my job. I work on JRuby full-time. I partner with all of these different JRuby users and folks that want to bring to their projects what JRuby can do. And I have JRuby stickers and business cards for you if you'd like to come up. Dziękuję. Thank you very much for your time. I think we're just about out of time for questions. I can jump over there.
Just maybe one of the questions.
Sure, let's bring that over here. There we go. Okay, so are you using a C-written parser now? Yes, this is our direction that we are going to be going. The parser that we're going to be using is shared with other Ruby implementations and written in C. The way that we're going to be able to use this even without a native library is a bit magical. We actually have a WebAssembly version that runs on a JVM WebAssembly implementation, performs reasonably well, but we have basically built a parser that can plug in either our old Java version or the C version and still generate all the same code. Second question here, benefit of stopping JIT compiler at tier 1. I would love if this wasn't the case. Tiered compilation was supposed to give us fast startup along with all the optimizations. The problem is that when you run with regular tiered compilation, it doesn't do the simplest code in tier 1. It goes to something called tier 2, which is simple code, but still has profiling information, still gathers info about your code, and still runs slower than that first tier 1. Then eventually it gets to fast code, but the fastest way to start up for us was to use tier 1. I'll take a couple more here. Panama, 2x speed up. I'm sure this can be faster than what it is right now. This is a fairly old number that I did last year. Just at FOSDEM a couple months ago, I saw a presentation where they showed JVM JIT code able to call directly out to a native stub, skipping all of JNI. Very exciting stuff, really hoping to see more improvements here. I think that's all the time I have. If you want any more questions, please come up and ask or just contact me directly. Thank you.